Hey guys, here's an example from central limit theorem. I'm going to walk through one of the examples from our class notes. One thing I want to point out really quickly before we begin this, it does not state it in the problem, but we are going to assume that the population is normal. So we're going to assume that the population is normal so we can use central limit theorem on individuals and on group data. Now, we'll just jump right into the problem. You need to obtain new desks for an incoming class of 25 kindergarten students who are all 5 years old. To prepare for this decision, you've obtained the following data on the heights of students. Sitting height is measured from the bottom of the foot to the top of the knee of sitting students. So here's my data. I've got it split up into two categories. I've got boys and girls, and I'm going to be utilizing this data in separate options for different types of problems. There's the boy data, there's the girl data. It shouldn't surprise you too much that the boy data is a little bit larger than the girl's data. Thinking about the population and the average population height, boys are a little bit taller than girls. Now, let's go ahead and jump right into the first problem. All right, the first problem is saying, what is the probability of picking a random female student with a sitting height less than 65 centimeters? So this is really nice because we've got a random female student. That tells me that I'm going to be looking for the probability of one individual student. Now that helps me out quite a bit. We already know that we're going to be using a normal curve, so I'm going to go ahead and draw me my normal curve here. Here's my normal curve. I'm going to go ahead and add to that middle of the curve my population mean. In this case, I'm looking at the population of girls and their heights, so I'm going to be looking at 61.2 centimeters. I've also know that the standard deviation in this case is going to be the standard deviation of my population, which is 3.1. So I'll go ahead and add that here as well. So here's all my data set up. The next part of the question is asking about the height of someone less than 65 centimeters. So I'm going to find where that 65 centimeters is on my data. I'll just estimate it to be right there. And I'm going to be looking for a region associated with that height. In this case, I know that I'm going to be looking for something less than that. So I'm going to go ahead and shade in the region over here to the left. And I'm looking for all of this blue region. So that blue region is the probability of picking someone less than 65 inches tall. So that's a really, really good thing. I've done everything that I can do at this point. I've added all the information to my graph. I've determined what region that I'm looking for. Now it's just time to find what I'm looking for. And in this case, what I'm looking for is I'm looking for the probability of one of those females being less than 65. Or in this case, I'm trying to find the area of that blue region. That's what I'm trying to determine. I've got two functions that allow me to solve these types of problems: normal CDF or inverse norm. In this case, I'm looking for an area. So the function that I'm going to use is normal CDF. And remember, normal CDF, it's going to ask for four numbers. It's going to ask for a lower number where you start measuring the area at. It's going to go to the upper, and then that's asking where we're going to stop measuring the area at. It's asking for the mean and the standard deviation. In this case, my lower, I'm starting all the way over to the left-hand side where this exists all the way over here where it's not even big at all. It's tiny, tiny, tiny. So I'm just going to put negative 10,000. Very, very small over to the left-hand side. I'm going to go to the upper, which is going to be 65 because I'm defined by that 65. My mean in this situation is my 61.2, and then my standard deviation is going to be my 3.1. When I type that into the calculator, I should get a value of 0.88986. That's a really important number because now I can determine what this really means in this situation. I can make this a percentage if I wanted to. It'd be roughly 89%. So if I wanted to solve this question in terms of a full sentence, I could say there's an 89% probability of picking a random female student and then being in that blue region or being less than 65 centimeters. So hopefully you can see that is how we solve these types of problems. Now, if I wanted to expand this type of problem, or if I wanted to ask further questions that kind of ask very similar things, I could write a very similar question. So let's look at this one right here, 5a kind of 2 here. What's the probability of picking a random female with sitting height greater than 65 centimeters? And what's nice is if we look to our graph, we can actually identify the answer to this very, very quickly. So we've already determined that the area under this curve that's highlighted in blue, that's less than 65 centimeters. So if I looked at this green area, I know that's going to be the area greater than 65 centimeters. And what's really, really cool is if I took the area defined by that blue curve and I added to, or the area defined by the blue highlighter, and I added to that the area defined to the green highlighter, I know that that region, those areas must be equal to one whole, because the idea of complements and their probability. So if I already know the area of the probability of getting something in this blue region is 0.89, that's the area. I figured that out by normal CDF just a second ago. I can just use simple arithmetic and say, well, then the area of this green region must be 0.11, because I know 0.89 plus 0.11, it must add up to one whole. And I just did some simple 6th grade algebra there. What I really did was 1 minus 0.89 to get that 0.11. But what that tells me is that tells me a lot of things. It tells me how to answer this type of question really quickly. It tells me that there's an 11% chance of picking a random female with a sitting height greater than 65 centimeters. That's really, really nice, because I know that those are complementary answers. Someone less than 65 centimeters of having an 89% chance, there's a complement to that being greater than 65 centimeters. So you know the percentage of that happening must be the complement as well. When you're dealing with one individual student, these problems can be very, very straightforward. We've been doing these since section 6.2, so types of problems like 5A should not be too difficult. I've added 2 more types of problems here for this. I've added 2 more examples for 5A that I'm not going to solve through with this video. You can solve them the exact same way. The only thing that's going to be different is going to be the data that you're inputting into the calculator, because now it's asking you about the boy or the male height. So it's the same exact situation, less than 65, greater than 65, but now base it on the boy heights. So what I'd recommend, if you're still having confusion about these types of problems, pause this video, solve 5A3 and 5A4 very quickly, and then replay the video and make sure you got it correct. Now, I'll give you a little hint. You only have to solve one of those, and I'm not going to tell you why. If you don't understand why you only have to solve one of those, rewatch this section one more time, but go ahead and try that on your own, and then play the video and see if you got it right. All right, so now you see the answers to those 2 solutions, or those 2 problems. 2 different ways to solve it, or the first one actually is straightforward. Normal CDF, negative 10,000 to 65. You're measuring the area from negative 10,000 up to 65. And then you've got your mean and standard deviation of that data. You get an 86% chance of finding a male student less than 65 centimeters. The opposite one, it's the idea of taking that height and looking for that height or taller. So we start at 65 and go up to 10,000. Typing in the mean and the standard deviation will give you 13.49%. Or you could also just think about complements. So this is that advanced way to think about it. You could say, okay, well, I know that less than 65 centimeters and greater than 65 centimeters must be complements. So once I figured out one, I can just do a quick calculation to get the second one. Both of those solutions will work, and hopefully you feel much better about solving types of problems like this. All right, so now let's get to a real good example about central limit theorem. Here we've got a situation where we're trying to find the sitting height that will accommodate 95% of the males in the class. And if you don't know which curve we're going to be utilizing to solve this one yet, hopefully it'll make sense to you as I work through this. Because what I'm going to do is I'm going to pretend that I don't know which curve to look at. And I'm going to set up the problem with 2 different curves. Now, when I say 2 different curves, remember, we're assuming normal distribution for our population. So I've got a normal curve based on my individual data, and I've got a normal curve based on my sample data, my sample group data. So what I'm going to do is I'm going to go ahead and identify this first curve, and I'm going to put my mean on the curve. My mean in this case is going to be 61.8, because I'm talking about the males in this case, so 61.8. And I know my standard deviation of the males is going to be 2.9. So I'll go ahead and add that value there as well, 2.9. In this case, well, let me come back to that in a second. I'll go ahead and add my data for my second curve as well. My second curve is going to be very similar, but it's going to be a little bit different. Remember, this is the mean of these samples, and this is the standard deviation of these samples. So it's a little bit different. My standard deviation of the samples is going to be the standard deviation of the population divided by the square root of n. And then my mean of the samples is going to be the same as my mean of the population. That just turns out to be that case. So I can go ahead and add my data to that on my curve. That's also 61.8. But it's really important here to identify that these are measuring 2 different things. These 61.8 are not the same 61.8, and you've got to think about it in different terms. The 61.8 on the left-hand side is actually measuring the height of individuals. And the curve on the right is measuring the average height of samples from the population. These are 2 totally different things. The one on the left is taking in account for individual people as they're being determined in the population. The one on the right is taking samples of the entire population and averaging the height of everyone in that sample. So you've got to determine which one of these you want to use to answer the question. And it's really important because these standard deviations, they may look very, very similar, but they're not. That dividing by the square root of n is going to throw off your answer quite a bit if that's not the right one you're supposed to use. So take a second and think to yourself, which one of these curves should you use to solve the problem? Hopefully you've come up with an idea. If you haven't, pause the video, think about it a little bit longer, make a guesstimation, and then resume the video. So if you have not determined that you need to be utilizing the first curve on this video, think about what's going on again. You're looking for the height of you're looking for a height that will accommodate 95% of the males in the class. When we're looking for this height, we're looking for the 95 males as individuals. We're not looking at, we're going to grab a sample of 25 students in the classroom. There's no sampling at all. The key thought here is sample. There's no sampling, so we're not going to use the sample curve. So we're going to utilize the curve on the left-hand side, and what we're looking for is the height that will accommodate 95%. Now, this problem does get a little more complicated. It steps into another area that we haven't done a ton of examples with. It's asking for the height that will accommodate 95%. Well, where is height located on my curve here on the left-hand side? The height is located along the x-axis. So what I'm really looking for is I'm looking for an x value. And in this case, I'm looking for the value that is determined and makes the separation between 95% of the data. So what I'm going to do is I'm going to go ahead and shade in where I see 95% of the data on this curve. And it comes up to this random point right here. I know that this value, whatever this value is, separates 95% of the data. That yellow area is defined as 95%. Now, I don't know where this value exists. That's the tricky thing. I don't know where that is. So I've got to find that value. So what I've got here, I've got a situation where I've been given the area. I know the area, but I don't know the x value, the data value. Luckily, we have a function in our calculator, inverse norm, that will do this exact thing. It will take an area, and with that area, we have to define a mean and a standard deviation, but then it's going to give us a data value. That's what inverse norm does. It takes the inverse of the area under the curve. So this is going to give us a data value. If we type in our situation, our 95% and our mean and our standard deviation that we've been given, we get the calculation inverse norm of 0.95, 61.8 for the mean, 2.9 for the standard deviation. And when you type that into the calculator, you get a nice 66.57. So what that means here is that if you go back to the curve over here, I've got my region defined by 0.95% of the data. And I've got that value that I figured out by using inverse norm. So I know anyone lower than a height of 66.57 centimeters is going to be within that 95% of the population. Anyone above a height of 66.57 centimeters is going to be in this upper 5%. That tells me that if I picked a desk height of 66.57 centimeters, then 95% of my population would be below that height. So it would fit 95% of my population. That's an excellent height to pick because then I've got only these 5% of outliers that I have to worry about in the classroom. You've got to understand what's going on. If I were, for example, using this curve over here and I determined that 66.57 was defined by my 95%, all that would say is that 95% of my groups would have a mean of 66.57. And that doesn't make any sense because this original conversation, the original question, said nothing about groups. So again, this type of situation is not what I wanted. Hopefully you're understanding how to solve these types of problems and you're seeing the differences between the two. If not, we've still got a few more examples to go through. Okay, 5C. What seating height is greater than 95% of the means of seating heights from random samples of 25 male students? That sounds like a mouthful, but it's actually true. I'm going to set up this problem like I did the previous one where I've got two normal curves and we're going to determine which one to use. So here I've got both curves set up, and I'll go ahead and zoom in and walk through both of these. The left-hand side, I've got the curve set up for my entire population, the heights of individuals. I've got the mean and the standard deviation graphed on my curve, and I know that it's normally distributed because it is a normal population. I assume that at the very beginning. On the right-hand side, I've got a very similar normal curve, and on this curve, it's a sample curve. So it's talking about the average heights of each sample that I've pulled in. Notice that my mean is the same as the mean of the population. That's part of the central limit theorem. And my standard deviation has changed. It's being altered by the standard deviation divided by the number of people in the sample. If I went ahead and calculated the standard deviation in this situation, I'd get a value of 2.9 over the square root of 25. When I type that into the calculator, I should get an estimation of 0.58. So there's my standard deviation of the sample group means. Now, if I'm looking at these two situations, these two normal curves, I got to determine which one I want to utilize to solve this question. Now, let's go back to the question itself. The question's a little wordy, but it's saying, what sample height is greater than 95% of the means of sitting heights? That's right there, it tells me what I'm looking for from random samples of 25 male students. So this is the key word, the means of sample of sitting heights. That's telling me I'm looking for a mean, an average, and I'm looking for that average from a sample of 25 male students. That should be telling me right away that I'm looking for the average heights of a sample. I do not need to look at the data curve for the heights of individuals. So I'm going to be looking at the curve on the right-hand side. And I've even got an additional value because I know that I'm going to be looking at samples of 25. So I know that my value for my n that I'm going to utilize for several of my calculations is going to be 25. I do notice that I kind of I let the cat out of the bag here in the middle. I let you guys go ahead and see what was really going on. But that's okay. For the sake of the problem for now, we know we're utilizing the curve on the right-hand side. Let's go ahead and solve the problem. So I've been asked to find the sitting height that is greater than 95% of the means of sitting height. So let's go ahead and look at my curve. And I know that 95% of my heights are going to be defined by some value along this x-axis. Some value, I don't know what that value is, but I know that 95% of my data is going to be over here on the left-hand side in this green curve. That's 95% of the data. Went ahead and identified what that area is, or what we're claiming that area to be. The thing is, we don't know this value that defines that region, and that's what we have to determine the answer to solve the problem. We've been given an area, we've got to find the value for that region. Luckily, we've got a calculation, a function in our calculator that allows us to do that. If we look at inverse norm on the calculator, it's going to ask for three values. It's going to ask for an area defined to the left, as well as the mean that we're looking for, and then the standard deviation. In this case, we know that our mean and standard deviation are referring to sample populations, but we know that our area is going to be just 0.95. Our mean in this case is the same as our population mean, 61.8. And our standard deviation, we've calculated it above there, and that's also going to be 0.58 from before. When you type that into the calculator, you should get a value of 62.75 centimeters. So it's really important you understand what this value is representing. This is saying if you took the average of 25 students' heights, that average 95% of the time will be below 62.75. It's not saying that 95% of the students will be below 62.75. It's saying the average of 25 students will be below that 62.75 95% of the time. 5% of the time, the average of 25 students will be above 62.75. That's what's defined here in this yellow line. But you've got to identify what this value is really saying. On average, the average of 25 students, that average will be below 62.75 95% of the time. Last problem. When you make a decision about your desk order, which question will be more valuable, 5B or 5C? So here I've pasted in this conclusions from 5B and 5C. I'd recommend you reversing the video and watching those parts of the video if you haven't watched those yet. But on the left-hand side, what I've got is I've got the region of 95% of the individuals, and I've got the height defining that region. 66.57 centimeters is the height that defines the top 5% or the bottom 95%. So anyone above that measurement, and I'm talking about the measurement right here, anyone above that measurement of 66.57 is in the top 5% of the population. Now, on the right-hand side, I've got a similar type of conclusion, but now I'm looking at the average heights of students in the sample. So what I've got is I've got a sample of 25. I'm grabbing 25 students at a time, and I'm averaging those heights. Well, on average, 95% of those are going to be defined by the height of 62.75. And it's really key here to remember what's being measured along the x-axis. On the left-hand side, I'm looking at the height of individual students. On the right-hand side, I'm looking at the average heights of the sample. So on the right-hand side, I've got an average height of 62.75. That's great. That tells me a lot, but that doesn't tell me anything about the individual students. If I'm trying to make a decision based on what desks I want to order, I'm more interested in the heights of the individuals, not about some value that determines the middle number of 25 students. And that's really what the average is telling me. It's some type of just explaining the middle number. So in this case, I'm interested in the result from 5B because it's talking about individual students. And if I'm looking for desk sizes, I'm going to want to determine if I can meet or reach my individual students. I'm not worried about the average height overall. This is a good value to tell me something in the middle, but it's not going to be a good value for me to kind of estimate something along my class.